Alright guys, let's go over this motion graph practice. Before we do so though, I want to review what is on our kinematics graphs reference sheet, because we're going to be using that during this video. So on one side we have our different types of graphs. We have our position graphs and velocity graphs. On the top here we have graphs that are moving right. All those position graphs are upward sloping, they're increasing. And all those velocity graphs are above the x-axis. If I'm moving left or down on this bottom row, all those position graphs are decreasing, going from top left to bottom right, and all my velocity graphs are in the negative region, which is below the x-axis, because negative velocity means moving left for us. If we go to the second page, or turn that page over if we have the printed out version, we have some different characteristics of some graphs we can look at, and in the table, it has what it means for each graph type. So first I look at the value of the slope. The slope of a position versus time graph would give me the velocity of that object. The slope of a velocity versus time graph will give me the acceleration of that object. And then if I have an acceleration graph, the value of the slope there doesn't really tell me anything that actually is a value. It's called the jerk, but we do not talk about that in this class. The way it slopes on a position time graph tells us the direction of motion, if it's going up or down or left or right, depending on the situation. If a velocity time graph is sloping towards the x-axis, those numbers are getting closer to 0, so that means the object is slowing down. If it's sloping away from the x-axis, that means those numbers are getting larger. That object would be speeding up. Which way it slopes for an acceleration versus time graph, again, doesn't really tell us anything. And as we're going to see, our acceleration versus time graphs are going to be horizontal lines. It just changes depending on the value of the acceleration. So next we get to something called the area between the graph and x-axis. For a position versus time graph, that tells us nothing. For a velocity versus time graph, that tells us the displacement. Basically, how far from the starting position is that object, is the displacement. I can get that from a velocity graph. If I take the area of an acceleration versus time graph, that can actually give me the change in velocity. It won't give me the velocity value, but it can tell me how much my velocity increased or decreased in a time period. If I read the vertical axis value, basically what the y-axis is telling me at a certain point in time, position versus time gives you position, velocity versus time gives you velocity, and acceleration versus time gives you acceleration. And then finally, if the graph is above or below the x-axis, on a position graph, all that tells us is where the object is in relation to wherever we're setting our 0. If it's below the x-axis, it's to the left or down from our 0. If it's above, it's to the right or above our 0 value, if we put a number line on our problem and set somewhere to be 0. On a velocity versus time graph, above or below the x-axis will tell us which way it's moving. If it's above, those are positive velocities. Those are moving up or down, up or right, depending. And then below the x-axis are negative velocity values. Those would be either moving left or down, depending on the situation. And then if the acceleration versus time graph is above or below, that will tell us if something is speeding up or slowing down. But I also have to know which way the object is moving. So the acceleration graph by itself cannot tell me if it's speeding up or slowing down. That in combination with velocity can tell me if it's speeding up or slowing down. If you need a refresher on that, go watch video 0108 about direction of acceleration and how that tells us whether it's speeding up or slowing down. Mr. P does a great job explaining that in that video. So now let's get to our problems. And I apologize in advance, I have no idea how long this video is going to be. We're just going to make it work. So number 1, the graph below describes the motion of a fly that starts out going right. For us, let's change right to be left, because I can see my graph starts out in the negative region, which for us is a negative velocity. So I'm going to change that to left. Should have caught that before I printed it out. Section C stops when the line crosses 0, the same with section F. What does that mean? There's a difference here between C and D, and we'll see why when we start answering our questions. but as soon as that graph crosses the x-axis, it changes from C to D. Same thing over here. Above the x-axis is F, and below the x-axis is G. So let's look at our problems. Identify the sections where the fly moves with a constant velocity. So what I have to realize here is I'm given a velocity graph. So if my velocity is constant on a velocity graph, that means it's not changing. So any sloped section on a velocity graph, my velocity is changing. So where does it move with a constant velocity? Well, section B moves with a constant velocity. That is a constant velocity of -10. These numbers are a little bit off. Each of these lines, these markers, is 5. So that's where those should go. So the second line down, that would be a -10 meters per second. So that's moving with a constant velocity. You could also say that I also applies. They would apply because it's a flat section of the graph, so my velocity is not changing. But if I'm thinking about where something moves, I has a constant velocity of 0. If my velocity is 0, I'm not moving, so I would not include I in this answer. It would just be B. If that condition of moving was not there, if it just said where does it have a constant velocity, then I would say B and I. But it does say it has to be moving. So where does the fly move right, slowing down? So the move right here, since it's a velocity graph, means it needs to be above 0. It needs to be above the x-axis. If it's slowing down, it needs to be sloped towards 0. So it needs to be above the x-axis, and it needs to be approaching 0. There's only one section that I see that does that, and that is section F. F starts at 15, ends up at 0, so that must be slowing down, and it's moving right because those are positive velocity values. So now the opposite. What if it's moving left and speeding up? So that would be below the x-axis, below 0, and sloping away from 0. And I'm getting these from that chart we just talked about a few minutes ago. So below 0 and sloping away from 0. Well, I can see A does that, and G does that as well. And those are my only two sections for that answer. Part D, when is the fly at rest? We kind of answered this in Part A. Where's my velocity 0? My velocity is 0 during section I. So now we get to some calculations. What is the average velocity of the fly between 0 and 15 seconds? Well, how do I calculate the average velocity of something? To get average velocity, I take the displacement divided by the time. So for us, the time here is going to be 15 seconds. Now the question is, how do I get displacement from a velocity graph? Well, if we look back at our reference sheet, to get displacement from a velocity graph, I take the area underneath the curve, or between the curve, between the graph and the x-axis. So I want to do this from 0 to 15 seconds. So I'm going to stop at 15 seconds, taking the area. So how do we do this? How do I take the area of this graph? Well, from 0 to 6 seconds, my graph is below the x-axis. So I want to take the area of this shape between the graph and the x-axis. I want to take the area of all this. We're going to talk about how to do that in just a second. But that's not all the way to 15 seconds. After 6 seconds, the graph switches to above the x-axis, and now I can take the area of this shape. So I can see one of these areas is below the x-axis and one of these is above. What does that mean for our displacements? Well, let's talk about that once I get done shading in this area. That's good enough. Okay. So this area from 0 to 6 is a trapezoid. off the top of my head, I don't know the formula for the area of a trapezoid. What I do know is I know the formula for area for rectangles and triangles. So I want to split these areas up into things I can take the area of. If I look at the red area here, I see there's a huge rectangle here, and that leaves me with 2 triangles I can take the area of. So let's start taking the area of these shapes. So from 0 to 2 seconds, I have this triangle right here. If I want to take the area of that triangle, it's going to be 1/2. The base of that triangle is 2, and the height, that graph goes down, or that triangle goes down to -10. So I'm going to put -10 in my area formula. I want the area to be negative because I know this is moving to the left, which is in the negative direction. So if I multiply that out, I get the area of this triangle is -10 meters. The area of this rectangle is base times height. So the base of this rectangle in section B is 3 seconds. Again, the height is -10, so that has an area of -30. This triangle here by C, the area is 1/2, the base is 1 second, the height is -10 meters per second. Multiply that out to get the area of that triangle, and I get -5 meters. So let's go to the red. This triangle, by part D here, is 1/2 times the base of 1 times the height of +10. That's going to give me +5. This huge rectangle here, it goes from 7 seconds to 15 seconds. So that has a base of 8, and the height is 10 meters per second. Multiply those together, and I get 80 meters. And then up here, finally, this last triangle. The base is the same as that rectangle, which is 8, and it goes from 10 to 15, which gives me a height of 5. Did I do this right? I believe I did. So that would make this 20. So now, how do I get the overall displacement by looking at this graph? Well, I've got all these individual displacements. I'm just going to add them together. If I add -10, -30, -5, +5, +80, and +20, I get an overall displacement of 60 meters. So that means from beginning to end, from 0 to 15, I ended up 60 meters to the right of where I started. And I can sort of see that by seeing that this red area is greater than the blue area, so I should end up to the right of where I started, because I went to the right more than when I went to the left. So if that's my displacement of 60 meters, I'm going to put that in my equation, and then I just have to divide 60 by 15, which would be 4 meters per second. And notice that is a +4 meters per second. So what was the distance traveled by the fly in this time interval? Well, my displacements can be negative. If I want to calculate distance, though, I just leave off the negatives. I don't care whether I'm moving left or right. It's all positive when I'm calculating distance. So if I do 10 plus 30 plus 5, which would be 45, plus 5 is 50, plus 20 is 70, plus 80 would be 150. So add all those together, ignoring negatives, and you get the distance. So velocity equals 4. Distance was a total of 150 meters. Moving right along here. G, what is the average speed of the fly in the same time interval? Well, what's my speed formula? Speed equals distance over time, the same time interval being 15 seconds, and we just found the distance of 150 meters. So you do 150 divided by 15, and I get a speed of 10 meters per second. What is the average acceleration of the fly in this time interval? Well, our formula for acceleration from the first video this week on Monday is acceleration is change in velocity over change in time. So my time My final time was 15 seconds. My initial time was 0. That gives me the change in time. My final velocity at 15 seconds, if I read the velocity at 15, that velocity is 15 from the graph on the previous page. The graph starts at 0. So my final velocity was 15, my initial velocity was 0. So I get 15 divided by 15, which is 1, and the acceleration, the units, since I'm dividing by seconds again, is meters per second squared. Or you could write meters per second divided by another second. So meters per second per second. So what's the total displacement of the fly from 0 to 22 seconds? Well, I already know from 0 to 15 is 60 meters, so I just need to figure out what's the displacement from 15 to the end. So going back to our graph here, displacement from 0 to 15 is 60. So now let's figure out what's the area of this shape from 15 to 18, and then what's this shape down here? What's that area? Which is going to be negative because it's moving to the left. All right, this little triangle around F here. The base of that triangle is 3. So I got 1/2 times 3. The height of that triangle is 15. So whatever 1/2 times 45 is, which would give me 22.5. Then this triangle here is 1/2. The base is 3 seconds, and the height is -5. So that's going to give me an area of -7.5. So I know everything to the left here is 60. So to get the new displacement from all the way to 22 seconds, then I'm going to add 22.5 to that because that's positive, and subtract 7.5 from that as well. So 60 plus 22.5 minus 7.5 gives you a total displacement of 75 meters from beginning all the way to the end. So our displacement here is 75 meters. Now we can move on to the next question. Identify the times when the fly changes direction. Well, the fly changes direction anytime the graph crosses the x-axis because I'm looking at a velocity graph. So those times are 6 seconds and 18 seconds. You can think that 21 seconds it changes direction, but it doesn't actually cross the x-axis. It goes to the x-axis, which is 0, and stays there. So it doesn't actually change directions, it just stops. So that's why I only have these 2 times where it changes direction. Which brings us to question K. We want to draw an acceleration versus time graph for the fly. So an acceleration versus time graph is going to basically describe to us the slope of a velocity versus time graph. So the slope of this graph equals the acceleration, if I can spell acceleration. So I just need to find the slope of each section and graph that on the graph below. So in section A, let's go section by section. Section A, from 0 to 2 seconds. The run here is 2. The rise is -10. So the slope of A would be -5, and that lasts for 2 seconds. So an acceleration of -5 for 2 seconds. Then, in section B, the run is 3, but the rise is 0. So that would be a slope of 0. So my graph just goes straight up to 0 in a stair step like that. Now in the video on graphing, he did talk about how this is ideal data. In reality, there will be some curves here, but our velocity graph immediately goes from one slope to another, so our acceleration graph immediately goes from -5 to 0. And that's how our acceleration graphs are going to look. They're just going to be horizontal sections, and I'm just going to be at 0 or some other value. You're never going to have a sloped acceleration graph for us in this class. So after 5 seconds, C and D is one straight line. So I'm going to combine those and find the slope of that one straight line. Well, the run is 2. The rise goes from -10 to positive 10, which if I go that entire distance is a rise of 20. So rise over run, 20 over 2, I get a slope of 10. And that 10 is for 2 seconds. So for 2 seconds after that, slope of 10. Now E. E is this segment. What is the run of E? Well, it goes 1, 2, 3, 4, 5, 6, 7, 8 to the right. And then 1 box up, but the rise isn't 1. The rise is from 10 to 5, or 10 to 15, which is a rise of 5. So 5 over 8 is a slope of 0.625. So it's not 0, but it's very close to 0. So I'm going to put the line just a little above and go all the way to 15 seconds. And we pretend that is straight. So now we get to F. F is this section. The run is 3 seconds. The rise is negative 15. It goes from 15 to 0. So negative 15 divided by 3, that is a slope of negative 5, and that goes from 15 to 18. Now G is 2 seconds. So the run is 2. The rise is negative 5. It drops from 0 to negative 5. So negative 5 over 2 is negative 2.5. And I draw that for 2 seconds. Then H here, the rise, or the run is 1, the rise is 5. So that is a slope of 5 for 1 second. And then finally, section I here at the end is a horizontal line that has a slope of 0. So there's our completed acceleration graph for this motion. So now this leads us to problem 2. Little Joey plays with the remote control car and generates the motion graph below. The car starts by moving eastwards. Section B stops when the line crosses 0, same with section E. So this is a position graph. So I feel like this graph is easier to deal with and easier to see where this information is coming from. Identify the sections where the car moves with a constant velocity. Again, just like in the last one, moves is key here. It has to be moving, and that motion has to be constant. Which of these sections are not moving? Well, D is staying at negative 10 meters. That's not moving. And neither is H, because H is this flat section here. So that means what is moving is A, B, C, E, F, G, I, J. How do I know all those are constant velocity? Well, all their slopes are constant. There are no curved sections on this graph, so the velocity during those sections does not change. So how do I know when the car is moving west? Well, west for us is going to be a negative direction. On a position graph, the direction of the slope tells me which way it's moving. So any positively sloped sections are moving east. Any negatively sloped sections are moving west. So that would be for us B, C, G, and I. Now C, identify any sections where the car speeds up. Well, to speed up, I would have to change velocity, which we just said earlier is constant in all of my sections. So there are no curved sections of this graph. There's no slope increasing or slope decreasing. So you could think of this as kind of a trick question because there is none. There are no sections where the car speeds up. When is the car at rest? We kind of answered this when we answered A. It's pretty much any section that's not listed in A. So those would just be D and H because they're flat lines. They're staying at the same position. If you're staying at the same position, you're not moving. Let's move on. E, what is the average velocity of the car between 0 and 15 seconds? Same question as the last one, or the last problem. Velocity is displacement over time. So the time is 15 seconds. Now what's my displacement from 0 to 15? So since this is a position graph, displacement is just final minus initial position. My initial position is 0. My final position at 15 seconds, not the very end, at 15 is 5. So on a position graph, displacement is very easy to find. You just take initial and final position, you do final minus initial, and I get a displacement of 5 meters. So 5 divided by 15 gives me a velocity of positive 0.33 meters per second. What is the average speed of the car in the same interval? Well, remember, speed is distance over time. So still 15 seconds, but now I have to find the distance from 0 to 15. That takes into account all these sections and how far they moved. So let's add them up. Section A goes from 0 to 10. That has a distance of 10 meters. Section B goes from 10 to 0, which is also a distance of 10. Displacement would be negative, but if I'm just counting distance, that's 10 meters. Section C, from 0 to negative 10, is still 10 meters. Section D doesn't move at all. That's 0. Section E, well, it actually looks like Section E goes all the way across 0. That's my mistake. Section E goes from negative 10 to 5, which is 15 meters, and that's where I stop because now I'm at 15 seconds. So 10 plus 10 plus 10 plus 15 gives me a distance of 45 meters. 45 divided by 15 gives me a speed of 3 meters per second. So now H, what is the total displacement of the car from 0 to 22 seconds? Well, again, let's get rid of this other one. Displacement is final minus initial position. My initial position at the beginning is 0. At 22 seconds, it ends up at negative 5. So that's my final position. So what's negative 5 minus 0? That's a displacement of negative 5 meters. That means at the very end, it is 5 meters west of where it started. So now let's draw a velocity graph. Let me group these real quick. Well, let's just get rid of that. Okay. So now draw a velocity graph describing the motion of the car from this position graph. So just like last time, to get velocity from a position graph, I take the slope. So the question is, what's the slope of each section? So in section A, I'll do this in blue. The run here is 3 seconds. The rise is 10. What's 10 divided by 3? That's a slope of 3.33 meters per second. So that's for, that is 4 seconds. My bad. What's 10 divided by 4? 2.5 meters per second. So for 4 seconds, I'm going to graph 2.5 meters per second. That's my velocity in section A. Notice it's positive. It's moving east. That matches what my position graph says. B and C are part of the same line, so I'm going to combine them together. The run here is 3, and the rise is from 10 to negative 10, which is negative 20. So what's negative 20 divided by 3? That is negative 6.67 meters per second. So it has to be negative and a little bit greater than 5. This is for 3 seconds. I'm going to say it's right about there. Section D, very easy. For the next 5 seconds, the slope of this line is 0. So for the next 5 seconds, from 7 to 12 is 0. Section E, the run is 3 seconds, and the rise is from negative 10 to 5, which is 15. Divide those two, and the slope here is 5 meters per second, and that's for 3 seconds. F has a slope of 0. So we'll, from 15 to 18, we'll say that is a velocity of 0. I think I made a mistake earlier on the last page. We'll go back and correct that. If we go to section G, the run here is 1 second. The rise is -5 from 5 to 0, and so that is a -5 meters per second for 1 second. H has a slope of 0, so velocity of 0 for 1 second. I, in 1 second of run, drops from 0 to -10. So that slope is -10 from 20 to 21. And then this last section J here, the run is 1 second and it rises 5. So that is a +5. So notice the same thing here. I can have stair steps of velocities because what my position graph is telling me is my velocity is immediately changing from one to another. I know this wouldn't happen in real life, but it's easier to think about and visualize this way without all the curves. And so we do that with these graphs. All right, before we end here, I definitely did make a mistake on this first page, and I realized it when I was actually finding the velocities. And the mistake here is with part D. I said only D and H were sections where the car is at rest, but I completely forgot about section F up here. That also has a slope of 0. It's staying at 5 meters, so there should also be F as an answer for this question as well. Hope this video is helpful. Remind me or message me, email me, do something, send smoke signals if you're having trouble with this. This is all we're going to be covering next week up until next Friday, which is our next test. So please, please, please do the Match That Graph Concept Builder, do the graphsandtracks.com. All those things can help us prepare for this test next Friday.